Welcome! In this session, we will dive into LeetCode problem number 1724. While the exact problem details are unavailable, we will explore potential approaches and outline strategies to tackle similar challenges. Let's get started. I am unable to access the details of LeetCode problem number 1724. I apologize, but I cannot access the actual LeetCode problem number 1724. Without the exact problem statement, input-output specifications, examples, and constraints, I cannot generate a comprehensive explanation. Please provide additional details or refer to the LeetCode platform for more information. When approaching an unknown problem, it's useful to consider multiple strategies, starting with a brute force approach. This method involves exploring all possible solutions to ensure correctness, even if it's not the most efficient. For instance, if the problem involves searching or sorting, we could use nested loops to exhaustively search through all combinations, which generally results in a time complexity of n squared. Alternatively, we might apply a basic sorting algorithm like bubble sort if the task requires ordering elements. While brute force guarantees accuracy, it quickly becomes inefficient as the size of the input grows. This approach is often the simplest to implement, making it a good starting point for smaller datasets or initial problem exploration, but it's important to recognize its limitations in terms of scalability. Now, as we think about optimizing our approach, we can consider strategies that leverage the structure of the problem to reduce computational overhead. For example, divide and conquer techniques work well for problems that can be broken into smaller, independent subproblems, such as binary search or merge sort. Dynamic programming, on the other hand, is ideal for challenges with overlapping subproblems, where storing intermediate results can significantly cut down redundant computations, as seen in shortest path or knapsack scenarios. A greedy algorithm might be appropriate when the problem allows for making decisions that are locally optimal, which can lead to a globally optimal solution. Additionally, if the problem involves graphs, we might apply algorithms like Dijkstra's for shortest paths or BFS and DFS for traversal. Alternatives like binary search are particularly efficient for sorted datasets, while hashing offers constant time complexity for lookups, making it a strong choice for tasks like detecting duplicates. The sliding window technique is another powerful tool, especially for problems involving contiguous subsequences, where it can transform a quadratic time complexity into linear time. Each of these approaches relies on understanding the problem's structure and identifying opportunities to minimize unnecessary computations. The chosen strategy ultimately depends on the problem's size and constraints. For smaller inputs, brute force methods are often effective because they are straightforward to implement and ensure correctness. However, for larger datasets, optimized approaches like dynamic programming, divide and conquer, or greedy algorithms become essential for managing runtime and memory usage. It's important to recognize the trade-offs here. Brute force is easy to implement but scales poorly, while optimized methods require more effort to design and implement but are far more efficient for handling large-scale problems. Alternatives like hashing or sliding windows can also be highly effective, though their applicability depends on the specific problem requirements. The choice of strategy is driven by the problem's demands. If correctness is the highest priority, brute force can be reliable. On the other hand, if efficiency is critical, understanding the problem's structure and leveraging the right optimized approach can significantly reduce computational complexity and improve performance. To start with, let's assume we're working on a grid-based problem. These types of problems often involve navigating through a 2D matrix while optimizing some aspect, like finding the shortest path, counting all possible paths, or maximizing a value such as the path sum. The grid can include various constraints. Some cells might be blocked, movements might be restricted to specific directions like up, down, left, or right, and there may even be associated costs for entering certain cells. The first step is to fully understand the problem and its constraints. For instance, understanding whether we're optimizing for distance, cost, or count will inform the approach. Next, we define the state. In most grid problems, a state can be represented as a tuple of coordinates, such as x, y, to mark a cell. If additional information like path cost or steps taken is necessary, this can be added to the state tuple. Clearly defining these foundational elements is key to building the algorithm effectively. Now that we've defined the problem and state, selecting the right data structures is critical for implementing the algorithm efficiently. A queue is a natural choice for breadth-first search, which is ideal for unweighted problems. For weighted grids, a priority queue, such as a min heap, is often used to prioritize cells with the lowest associated cost, making it suitable for algorithms like Dijkstra's. To avoid revisiting the same states and performing redundant computations, we use a visited set or a memoization table. This ensures we only process each state once or store results for reuse. The grid itself, represented as a 2D matrix, serves as the input, where each cell contains a value or weight. With these structures in place, the next step is initialization. We identify the start and end points in the grid and initialize the queue with the starting point, including any relevant data like the starting cost. The visited set or table is also initialized, and the start point is marked as visited to prevent reprocessing. The algorithm proceeds by traversing the grid systematically. First, we pop the front element from the queue. If a priority queue is used, this ensures that the state with the lowest cost is processed first. The current state is then examined to determine if it meets the target condition, such as reaching the endpoint or achieving a specific goal. If it does, we update the result, such as recording the shortest path or incrementing a path count. Next, we explore the neighboring cells in all valid directions, up, down, left, and right. For each neighbor, we check if it's within bounds, not an obstacle, and hasn't been visited or offers a better path. If these conditions are satisfied, the neighbor is added to the queue and marked as visited. This process continues until the queue is empty, ensuring that all reachable states are processed. Finally, the result is returned. Depending on the problem, this could be the shortest path, the number of valid paths, or an optimized value like the maximum path sum. If no solution exists, we return a special value, such as -1. There are several key insights to keep in mind when solving grid-based problems. Breadth-first search is particularly useful for unweighted grids since it guarantees the shortest path in terms of the number of steps. For weighted problems, a priority queue used with Dijkstra's algorithm efficiently finds the least cost path. Dynamic programming is another powerful tool, especially for counting paths or solving optimization problems like finding unique paths. It's also important to consider edge cases, for instance, very small grids like 1x1 or 1xn, grids that are completely blocked and offer no solution, or grids with negative weights, which require specialized algorithms like Bellman-Ford. The choice of data structures also plays a significant role. A queue is essential for BFS, while a priority queue is necessary for weighted problems. The visited set or matrix ensures states are not processed multiple times, and the grid matrix itself provides efficient access to the input data. To further optimize the algorithm, several techniques can be employed. Early exit is a simple but effective strategy where the search terminates as soon as the target is reached, saving unnecessary computations. For shortest path problems, heuristics like those used in the A** algorithm can prioritize promising states, significantly improving efficiency. Space optimization is another consideration. For instance, if the grid allows modification, the visited set can be replaced with in-place marking, reducing memory usage. Analyzing complexity is also essential to understand the algorithm's performance. For BFS, the time complexity is O(m*(n), because every cell is processed once, while Dijkstra's algorithm has a time complexity of O(m*(n) log m*(n) due to the overhead of maintaining a priority queue. In terms of space, BFS requires O(m*(n) for the queue and visited set, and Dijkstra's has similar requirements with additional space for the priority queue. These trade-offs between time, space, and optimization strategies are important to consider when solving real-world problems efficiently. This solution tackles a grid-based pathfinding problem using breadth-first search, BFS. The BFS algorithm is suitable for finding the shortest path in an unweighted grid. The grid is represented as a 2D list where zeros indicate walkable cells and ones indicate obstacles. The goal is to navigate from the top left corner to the bottom right corner. The shortest path function begins by initializing key variables. M and N represent the grid's dimensions. Directions defines possible movement directions, right, down, left, up. A queue, implemented with collections.deque, is initialized with the starting cell, 0, 0, and a step count of 0. A visited set tracks cells that have already been processed to prevent revisiting them. The BFS loop continues until the queue is empty. In each iteration, the current cell's coordinates and step count are dequeued. If the bottom right corner is reached, the function immediately returns the step count, ensuring the shortest path is found. For each cell, the algorithm explores its neighbors by applying the movement directions. Valid neighbors are within grid bounds, not obstacles, and unvisited. Valid neighbors are marked as visited and enqueued with an increment step count. If the queue is exhausted without reaching the target, the function returns -1, indicating no valid path exists. This implementation efficiently handles the shortest path search while avoiding unnecessary computations through the visited set. Here, we begin by defining the shortest path method, which takes a 2D grid as input. The grid represents our traversal space, where each cell can either be open, marked as 0, or blocked, marked as 1. First, we determine the grid dimensions, m and n, to establish boundaries for our traversal. Then, we define the directions array, which outlines the 4 possible movements: right, down, left, and up. This will help us explore the grid systematically. We use a queue to facilitate a breadth-first search, or BFS, approach, which is ideal for finding the shortest path. Each element in the queue represents a state defined by the current row, column, and the number of steps taken so far. Initially, we add the starting point, 0, 0, 0, to the queue, indicating the top left corner with 0 steps. To track visited cells and avoid revisiting them, we use a set called visited, where we store cell coordinates as strings, starting with 0, 0. The while loop begins our BFS traversal. As long as the queue is not empty, we dequeue the front element, which gives us the current cell's position and step count. We then check if the current position matches the bottom right corner, our destination. If it does, we immediately return the number of steps, as this represents the shortest path. If not, we proceed to explore the neighboring cells using the directions array. For each possible direction, we calculate the neighbor's coordinates, NX and New York, by adding the direction offsets to the current cell's position. Before proceeding, we ensure that the neighbor is within the grid boundaries and that the cell is not blocked. This is checked using NX equals 0, New York equals 0, NXM, New York N, and grid, NX, New York, equals 0. Once we verify the cell is valid, we construct its coordinate as a string, neighbor, and check if it has already been visited. If not, we mark it as visited by adding it to the visited set and enqueue it for further exploration, incrementing the step count by 1. The process continues until the queue is empty. If we exhaust all possibilities without reaching the bottom right corner, it means no path exists, and we return -1 as the result. This ensures that the function handles edge cases where the destination is unreachable. The BFS approach guarantees that the first time we reach the destination, we do so using the shortest possible path, making this implementation both efficient and robust for solving the problem. To solve this problem, we start by working with a simple 2x2 grid. The grid is initialized with zeros, meaning all cells are accessible. First, we determine the dimensions of the grid, which are m equals 2 and n equals 2. We define the possible movement directions as right, down, left, and up, represented as coordinate changes 0, 1, 1, 0, 0, -1, and -1, 0. We initialize a queue with the starting position 0, 0, and a step count of 0. This queue will help us manage the breadth-first search, or BFS. The visited set is initialized with the starting cell 0, 0, to keep track of cells we've already processed. In the first iteration, we dequeue the starting cell 0, 0, 0, and explore its neighbors. Moving right to 0, 1 is valid because it is within bounds, unvisited, and the grid value at that position is 0. We add 0, 1, 1 to the queue and mark 0, 1 as visited. Similarly, moving down to 1, 0 is valid for the same reasons, so we add 1, 0, 1 to the queue and mark 1, 0 as visited. At this point, the queue contains two positions, 0, 1, 1, and 1, 0, 1, and the visited set includes 0, 0, 0, 1, and 1, 0. In the second iteration, we dequeue 0, 1, 1, and explore its neighbors. The only valid neighbor is 1, 1, which is the bottom right corner. We add 1, 1, 2 to the queue with an updated step count of 2 and mark 1, 1 as visited. Next, the queue becomes 1, 0, 1, and 1, 1, 2, and the visited set now includes all grid cells. In the third iteration, we process 1, 0, 1, but find no new valid neighbors, so we move on to the next item in the queue. Finally, in the fourth iteration, we dequeue 1, 1, 2, which is our target cell. Since we have reached the bottom right corner, the minimum number of steps required to get from the top left to the bottom right corner is 2. This concludes the first example. In the second example, we have a 3x3 grid with obstacles. Here, some cells are blocked, indicated by 1s in the grid. The process begins just as before, by initializing m equals 3, n equals 3, the movement directions, the queue with the starting cell, 0, 0, 0, and the visited set containing 0, 0. In the first iteration, we dequeue 0, 0, 0, and explore its neighbors. Moving right to 0, 1 is valid, so we add 0, 1, 1 to the queue and mark it as visited. However, moving down to 1, 0 is not valid because it is blocked by an obstacle. After this iteration, the queue contains 0, 1, 1, and the visited set includes 0, 0, and 0, 1. In the second iteration, we process 0, 1, 1, and explore its neighbors. Moving further right to 0, 2 is valid, so we add 0, 2, 2 to the queue and mark it as visited. Moving down to 1, 1 is not valid due to an obstacle. Now, the queue holds 0, 2, 2, and the visited set includes 0, 0, 0, 1, and 0, 2. In the third iteration, we dequeue 0, 2, 2, and explore its neighbors. Moving down to 1, 2 is valid because it is unvisited and accessible, so we add 1, 2, 3 to the queue and mark 1, 2 as visited. After this iteration, the queue contains 1, 2, 3, and the visited set grows to include 1, 2 as well. In the fourth iteration, we process 1, 2, 3, and find that moving down again to 2, 2 is valid. This is our target cell, so we add 2, 2, 4 to the queue and mark it as visited. Finally, in the fifth iteration, we dequeue 2, 2, 4, which is the bottom right corner. The minimum number of steps required to navigate through this grid and bypass the obstacles is 4. The output for the second example is 4, as it takes 4 steps to traverse from the top left corner to the bottom right corner while avoiding obstacles. Now we examine a third example where no path exists. In this 2x2 grid, both possible paths from the starting position are blocked by obstacles. As before, we initialize the grid dimensions, movement directions, queue, and visited set. The queue begins with the starting position 0, 0, 0, and the visited set includes 0, 0. During the first iteration, we dequeue 0, 0, 0, and explore its neighbors. Moving right to 0, 1 is not valid because the cell is blocked. Similarly, moving down to 1, 0 is also invalid because of another obstacle. With no valid neighbors to add to the queue, the BFS ends. At this point, the queue is empty, which means there is no way to reach the bottom right corner from the top left corner. Since the BFS traversal is complete and no path was found, the output for this example is -1. This indicates that it is impossible to navigate from the starting position to the destination in this grid. This concludes our walkthrough of the examples for this problem, illustrating how the algorithm handles grids with varying complexities and obstacles. In this algorithm, we use breadth-first search, or BFS, to find the shortest path in a grid. To understand its time complexity, let's start by analyzing the traversal of the grid. In the worst case, where every cell in an m by n grid needs to be visited, the algorithm processes m*n cells. For each cell, we check its 4 neighbors up, down, left, and right, and since each of these checks is a constant time operation, the overall cost per cell remains 1. Multiplying this by the total number of cells gives us a grid traversal cost of m*n. Additionally, BFS uses a queue to manage the cells being processed. In the worst case, this queue can hold m*n elements, as it may contain all reachable cells. Each enqueue and dequeue operation is performed in constant time, 1, so the total cost of queue operations also amounts to m*n. When we combine these components, the overall time complexity of the algorithm is m*n. Now, let's look at the space complexity of the algorithm. The first contributing factor is the visited set, which keeps track of cells that have already been processed. In the worst case, where every cell in the grid is visited, the visited set requires O(m*n) space. Next, the BFS queue can also hold up to O(m*n) elements in the worst case, assuming all cells are reachable. Each element stored in the queue includes a tuple representing the cell's row, column, and the number of steps taken to reach it. This tuple's size is constant, so the overall queue space is still O(m*n). Finally, the input grid itself takes O(m*n) space, as it is directly proportional to the grid dimensions. Adding these components together, the total space complexity of the algorithm is O(m*n). Let's break down the best, average, and worst-case scenarios for this algorithm. In the best case, where the target cell is adjacent to the starting cell, BFS finishes almost instantly. It processes just one or two cells, resulting in O(1) time complexity, and the queue and visited set occupy only O(1) space. In a typical or average case, BFS explores a portion of the grid before reaching the target. However, if the grid size is large, the time and space complexity still approach O(m*n), as the algorithm may need to process a significant number of cells. In the worst case, BFS must explore the entire grid. This happens when no path exists or when the target is at the farthest possible cell. Here, both time and space complexity are O(m*n). Comparing this to a brute force approach, which might recursively try all paths, the difference is stark. A naive approach has an exponential time complexity of O(m*n) due to the 4 possible directions at each step, making it inefficient for large grids. BFS, on the other hand, is much more efficient because it processes each cell only once and avoids revisiting cells by using the visited set, reducing the complexity to O(m*n). To reinforce the time and space complexity results, let's look at a mathematical explanation. For time complexity, BFS ensures that each cell is processed exactly once. Each of these cells requires constant time operations for neighbor checks, enqueuing, and dequeuing. With m*n cells in total, the time complexity is O(m*n). On the space complexity side, the visited set and the BFS queue each store up to m*n elements in the worst case. This is supplemented by the input grid, which also requires O(m*n) space. When we sum up these components, the overall space usage remains O(m*n). This balance of time and space complexity makes the algorithm optimal for solving shortest path problems in grid-based scenarios. When solving problems, it's important to be mindful of common mistakes that can trip you up. One frequent issue is overlooking edge cases. For instance, if the input is empty, contains only a single element, or tests the extremes of the constraints, these scenarios can lead to runtime errors if not handled properly. An example would be array problems. Neglecting to address arrays of size 0 or 1 could result in index out-of-bound errors. Another pitfall is relying on inefficient approaches for large inputs. If the constraints are significant, say n greater than 10 to the power of 5, brute force methods with time complexities like O(n²) will likely fail due to time limit exceeded errors. Always analyze the time complexity to ensure your solution scales appropriately. Additionally, incorrect assumptions about the input can lead to flawed results. For example, assuming the array is sorted, elements are distinct, or values fall within a specific range without confirmation from the problem statement is risky. To avoid this, carefully read the problem and validate your assumptions with examples. Finally, don't ignore space complexity. Using excessive memory, such as creating additional arrays or hash maps, when an in-place solution is feasible, can lead to memory limit exceeded errors. Striking a balance between time and space efficiency is key to crafting a robust solution. Another common mistake to avoid is hard-coding values. This happens when you rely on specific test cases or fixed indices instead of writing generalized solutions, which can lead to failures on unseen inputs. For example, instead of dynamically iterating through an array, you might use specific indices, which won't adapt to different input sizes or structures. Now, shifting to interview scenarios, there are a few strategies you should keep in mind. First, identify patterns early. Many problems are variations of common techniques, such as sliding window, binary search, dynamic programming, or two-pointer approaches. Recognizing these patterns quickly can save you a lot of time. Also, it's crucial to explain trade-offs in your solution. For example, discuss the balance between time complexity and space usage when comparing approaches. Interviewers often value your ability to analyze these trade-offs. Additionally, a good strategy is to start with a brute force solution and optimize iteratively. Even if your initial solution isn't perfect, explaining your thought process and refinement steps is often more valuable than jumping straight to the optimal solution. Lastly, think beyond basic cases. For example, if you're working on a graph problem, don't just focus on simple connected graphs, consider edge cases like disconnected components or cyclic graphs. This kind of thorough thinking can make a strong impression in an interview setting. To deepen your understanding, it can be helpful to study related problems and patterns. For instance, the two-sum problem, LeetCode number 1, is a classic example of using hash maps for efficient lookups. Similarly, the longest substring without repeating characters, LeetCode number 3, is a sliding window problem that highlights how to handle constraints efficiently while minimizing space usage. Binary search, LeetCode number 704, demonstrates the power of divide and conquer techniques for efficient searching. Another key problem is maximum subarray, LeetCode number 53, which introduces Cadon's algorithm, a pivotal pattern for solving optimization problems. When approaching problems, you can consider alternative strategies. Brute force, while simple and often inefficient, is a good starting point for small input sizes or as a baseline solution. However, an optimized approach, which leverages techniques like hashing, sorting, or dynamic programming, can significantly reduce time complexity. For problems requiring in-place modifications, focus on space optimization to minimize additional memory usage. Finally, divide and conquer techniques are particularly effective for problems with recursive substructures, such as those involving sorting or binary search. The key takeaway is that solving problems effectively requires understanding constraints, handling edge cases, and optimizing iteratively. By practicing common patterns, you'll build the intuition needed to excel in interviews and tackle a wide range of challenges with confidence. Thank you for watching. Today, we reviewed approaches and insights for tackling LeetCode problem number 1724. Remember to focus on problem requirements and constraints when choosing a solution. Stay motivated, keep coding, and I'll see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!